Okay, welcome back to McNab Chemistry. Today we're going to have a look at trends in chemical properties of group 7 elements, but in particular we're going to have a look at the halides and their reducing powers. Okay, so the halide ions that we need to consider are the fluoride ion, the chloride ion, the bromide ion and the iodide ion. Okay, remember that halide ions form when a halogen atom, and halogens are in group 7, when a halogen atom gains an electron to gain noble gas configuration, i.e. a full outer shell. So for example, Cl gains one electron to form Cl-. So if we wanted to go from Cl- to Cl, the Cl- would need to lose an electron. Okay, so we need to consider the reducing ability of the halide ions, i.e. how good a reducing agent each one is. Okay, so when halide ions act as reducing agents, they themselves are oxidized. So 2F- or 2F- minus 2 electrons forms F2, 2Cl- minus 2 electrons forms Cl2, 2Br- minus 2 electrons forms Br2, and 2I- minus 2 electrons forms I2. Okay, therefore the halide ions, which are stronger reducing agents, lose electrons more easily. Okay, i.e. they are themselves oxidized more easily. Okay, so strong reducing agents are themselves oxidized, so strong reducing agents need to lose their own electrons. Okay, so the next question has to be which halide ion is the strongest reducing agent, i.e. which halide ion can lose electrons most easily? The answer must be the halide ion which has its outer electron most weakly attracted to the nucleus. Therefore, this must be the biggest one, which in this case would be the iodide ion. Okay. Remember, the outer shell electrons would be more shielded from the positive nucleus, okay, when the atoms are bigger. Therefore the outer electrons would be lost most easily. Okay, I should have said there, remember the outer shell electrons should be more shielded from the positive nucleus in the ion, isn't it? It's the chloride ion, iodide ion, bromide ion, fluoride ion. So the biggest ion, the distance between the outermost electron and the nucleus is bigger, therefore that electron will be lost most easily. So in conclusion, we would say that the iodide ion is strongly reducing and the fluoride ion possibly is non-reducing. Okay, so the fluoride ion is non-reducing because that is our smallest ion, and therefore it loses its own electron, its outer electron, least easily. So we're going to make this prediction that I- is a stronger reducing agent than Br-, which is a stronger reducing agent than Cl-, which is a stronger reducing agent than the F-. Okay, we now need to back this conclusion up with an experiment. Okay, and the experiment we're going to carry out is a reaction between the sodium halide and concentrated sulfuric acid. So for example, sodium iodide and H2SO4 liquid is concentrated sulfuric acid. Okay, right, if we think back to oxidation state, then we need to also remember that stronger reducing agents will cause the oxidation state of the species they are reducing to fall more. So if we take something like sulfuric acid, it contains the sulfate ion. Okay, the oxidation state of the sulfur in the sulfate ion is +6. So 4 times -2 is -8. We want to get up to -2. So what's the difference between -8 and -2? It's +6. So that sulfur is contributing +6. Okay. Right. So for example, focus on the S in the SO4 2-. Okay, SO4 2- can be reduced into a range of sulfur species. Okay, so SO4 2-, the oxidation state, is, as we've just said, is +6. The oxidation state of sulfur in SO2, sulfur dioxide, is +4. So 2 times -2 is -4. The overall charge on that species is 0. So if I'm at -4 and I want to get up to 0, the sulfur is contributing +4. Okay. The oxidation state of sulfur in atoms of sulfur is 0 because it's the element, and the oxidation state of sulfur in hydrogen sulfide gas, H2S, is -2. The H contributes +1, and there are 2 of them, so that's +2. Overall charge is 0, so if I'm at +2 and I need to get down to 0, then the S must be contributing -2. Okay, so if we think back to our halide ions and remember what the question is which halide ion is the strongest reducing agent? Okay, well, the strongest reducing agent will be the one that can reduce the oxidation state of a sulfur in the SO4 2- from +6 to an oxidation state of -2 of the sulfur in the hydrogen sulfide gas. So we're going to now look at our results table. Here we go. Yeah, so let's have a look at the results table for the reactions of sodium halides with concentrated sulfuric acid. Right, so the first reaction we do is the reaction between sodium fluoride and concentrated H2SO4. And when we carried out the reaction, except we didn't carry out the reaction, okay, but if you did carry out the reaction, we would observe steamy fumes of hydrogen fluoride gas, and a byproduct of the reaction there would be Na2SO4, sodium sulfate. Okay, right, so in my reactants I had the sulfur in the sulfate ion, so a +6 oxidation state, and in my products I had sulfur as the sulfate ion, a +6 oxidation state. So there's been no oxidation or reduction in that reaction at all. All that's happened is that the fluoride ion has gained a proton from the acid to form hydrogen fluoride. Okay, so the F- is acting as a base because it's gained a proton from the acid, so it's an acid-base reaction. If I look at the reaction between sodium chloride and concentrated sulfuric acid, exactly the same happens. I get my steamy fumes of HCl, sodium sulfate byproduct, sulfate ion there, oxidation state of the sulfur in the sulfate ion is +6 there. Again, the sulfate ion, oxidation state of the sulfur in the sulfate ion is +6. So therefore there's no change in oxidation state. It's definitely not a redox reaction. Okay, all that's happened is that my Cl- has gained a proton. So Cl- acts as a base because it's gained a proton, so it's an acid-base reaction. Okay, however, when I get down to the reaction between sodium bromide and concentrated sulfuric acid, suddenly extra things start to happen. First of all, I get the reaction that I've been getting above, so I get my steamy fumes of HBr, my acid-base reaction, but this time I get some colourless gas, okay, which is SO2, sulfur dioxide gas, and I get some brown fumes of bromine, molecular bromine, Br2. Okay, so I started off with sulfur in a +6 oxidation state in the sulfate ion, and then I got to sulfur in the SO2 with an oxidation state of +4. 2 times -2 is -4, got to get up to 0, so that's +4. So I've gone from an oxidation state of +6 to +4, so therefore my sulfur has been reduced, and in any redox reaction, when one species is reduced, another must be oxidized. So the Br- has formed Br2, so the Br- has lost electrons, it's been oxidized to form the Br2. Okay, so the Br- is acting as a reducing agent because it itself has been oxidized. Okay, so Br- could reduce the sulfur from a +6 oxidation state to a +4 oxidation state. Right, let's now have a look at the iodide ion. Okay, so the reaction of sodium iodide and concentrated sulfuric acid. This time I get my steamy fumes of HI. Okay, so that's just a simple acid-base reaction. I get some colourless gas of SO2, so +6 oxidation state of the sulphur in the SO4 2- has become +4 oxidation state of the sulphur in the SO2. But then I also get some yellow solid, which is the element sulphur, oxidation state of 0. Whew, so +6 down to 0 now. Then I get some gas that smells of rotten eggs. Okay, hydrogen sulfide gas, oxidation state of -2. Okay, so I've managed to reduce the sulfur from an oxidation state of +6 in the sulfate ion to an oxidation state of -2 in the H2S. Okay, so this was a reduction reaction, this was a reduction reaction, this was a reduction reaction. Well, in any redox reaction, if you have a reduction, you must have an oxidation reaction. Okay, so the I- formed I2. Okay, so the I- lost electrons to form I2, so that's my oxidation reaction. Okay, but we can see here that the iodide ion was able to reduce the sulfur from a +6 oxidation state right down to a -2 oxidation state. So the iodide ion is a stronger reducing agent than the bromide ion, which is a stronger reducing agent than the chloride and the fluoride ions. Okay, so let's go through our conclusion. So we can conclude from the experiment that the I- ion, the iodide ion, is the strongest reducing agent, as it was able to reduce the S, the sulfur, in the SO4 from a +6 oxidation state to a sulfur in the H2S with a -2 oxidation state. Neither F- or Cl-, so neither the fluoride ion or the chloride ion acted as reducing agents in this experiment, as the SO4 remained as SO4 throughout the reactions. Okay, and finally the Br- acted as a reducing agent, but only managed to reduce the sulfur in the SO4 from a +6 oxidation state to sulfur in the SO2 with a +4 oxidation state. So the bromide ion is a weaker reducing agent than the iodide ion. So in conclusion, we can most definitely say that the I- ion, the iodide ion, is the strongest reducing agent because it itself is most easily oxidized. Okay, that's it for today. Thank you for watching. I hope that's been helpful. Don't forget to like and subscribe and hit on the bell notification to stay updated.